Hi there and welcome to this new video. Now in this video I want to talk about something that goes a little bit outside the typical technical things that we see in computer science. So this goes into sort of like arts, into an artistic aspect of computer science. And what I want to talk about is quines. I want to talk about quines. Now what are quines? So here we have a quine.c program. So this is a C program. As you can see, it starts with the definition of an array of characters. Here we have all the different characters. And at the end here, we find the body of the program. Now, if we compile this program using GCC, right? We are just compiling this program. And if we execute this program, what we see is that this program prints out another program. Now, if we capture this output into a quine2.c, what is possible to see is that quine and quine2 are the same file. So this one is the same as this one, and indeed, if we do a diff on those two files, we get nothing, no differences whatsoever. So what we have here is a program that prints out its own source code. So this quine prints out its own source code because this quine was obtained from quine.c, and then this allows us to obtain quine2.c, and they are the same. So a program that prints its own source. Now this quine was written by Ken Thompson, a really key character in computer science, a key figure in computer science, and there is this paper called Reflections on Trusting Trust. And it is written by Ken Thompson, and here as you can see the title, it says, "To what extent should one trust a statement that a program is free of Trojan horses? Perhaps it is more important to trust the people who wrote the software." So this small paper, it's a 3-page paper, talks about trust, about software, and about how it is possible to introduce malicious code in software by hacking on the compiler and the tool chains of development itself. So basically, this is sort of like one of the first thoughts about supply chain attacks that recently we have heard a lot about. But in this context here, we're talking about attacks that can be done on the compiler itself. Now, as I was saying, Ken Thompson is like a key figure in computer science. He developed a lot of systems, he developed Unix, he worked most of his life at Bell Labs with his colleague Dennis Ritchie, who is the author of the famous book The C Programming Language. So these people are really amazing. They really played a fundamental, foundational role in computer science. Now, what I want to focus on this article for this video is on the quine that I've just shown, because Thompson in this video produces a 3-step attack, basically, in which in the first stage it talks about this program that self-reproduces itself. That is, they want to write a program, a source program, that when compiled and executed will produce as output an exact copy of its source. So that is what it comes with here, and here we can see this program itself. So we can see the definition of the char s array with all the different values, and then the body itself. Now, this sort of like blueprint, this can be used to produce many different quines, because between the array and the main, here we can put anything that we want, right? So that is the idea. Now, how do we produce such quine? So we can remove everything and we can start from scratch. And in this video, I'm going to show you how you can obtain such quine. So we start from the core structure of the quine, which is this code. So here we include the standard input output, we define the main entry point, and here we start to work some magic with the printf. Now specifically here the printf have two different roles. The first two printf statements here, they are used to print out the original array, right? The initial array of the file. The third printf here, the final printf, is used to print out the code itself, right? So we start with this. So let's put into a file, let's call it boot.c. So we have this boot.c. Now the next objective is to take this code and extract all the single characters of this code, including the new line characters. And to do that, we can use a simple Python wrapper here. So basically, what is the idea is that here we're gonna print the S array, right? The start of the array, the end of the array, and then here we're gonna open the file quine.c, and for each character in this code, we're gonna print out a tab character, the character itself as a string, and then a comma. And we do this with the function rep of c, representation of c, which means, for example, that if we find the new line character, this is gonna give us the new line as a string in C, right? So that's the idea. Now, as you can see here, though, before we open the quine here, we put a little header on top, and then here we put a 0 at the end. And it's gonna be critical to make this work out. So, if we execute this, here I'm running with Emacs, I can execute this. Actually, here I have to write boot.c because I've changed the name. Here I'm gonna execute this, and here I get a character with all the different characters indeed. So now I can copy this and I can put this into the source code. And by the way, I can also do it automatically, but right now let's just do it manually because it's just to show you exactly how it works. So basically, we have this file now. It's gonna indent everything. We have this file, which is composed of an array of characters and then a final piece of code. This final piece of code. Now, let's try to understand why this works. But before doing that, let's actually use it. Because the next step in the production of our quine is to compile this, right? I'm gonna compile into boot, I'm gonna execute boot, and when I execute boot, I get back another source code, right? Now this time, if you compare this with the original source code, what changes, as we can see, is that the final code here does not change, it's the same, and the array itself is almost the same, but instead of having the character, I have the integers. So I have the ASCII encoding, the ASCII numeral from 0 to 255, which represents the character itself. Like this 32 are the empty spaces, this 10 is the new line, this 59 is the semicolon, and so on and so forth. So now at this point we have this thing, and at this point, if we have this quine, here let's just call boot and we say quine.c. Now if we compile quine.c into quine, and then we execute quine to obtain quine2.c, and we do a diff between quine and quine2, notice that they are the same file, nothing changes. It means that our final quine is this quine.c. So technically speaking, boot is not a quine because the difference between boot.c and the output of boot is that in the output of boot we just have numbers, while in the source code of boot.c we also have the characters. But after that, from boot we obtain quine.c, and at that point quine.c is our quine program that outputs itself perfectly. Look at this. We are compiling it, we are executing and capturing its output, and then we are comparing the output of the program with the original source code, and they match perfectly. There is no differences between the two source files. Now, to understand this program, it's actually better to focus on the version with the characters rather than the version with the numbers, because it is a bit confusing to map out numbers to characters. So let's focus on boot.c and let's see why it actually works. So here we just define an array, but notice this element, right? This array does not start directly with the include statement, but it starts with a little preamble in which we have /t, 0/n, and then the closing of the array itself. And this is actually a key point to keep in mind, right? So when it comes to the final block of code here, what do we have? Well, we include the library, perfect. Then we have this, we declare this variable int I, at this point we are printing the start of the array. Here we are printing all of the bytes of the array until when? Until we meet the 0 byte, until we meet the end of the array. Now notice that at this point what we have printed is basically here. So if we have to construct the output, basically, let's say that here we have to construct the output, what we would have printed is this thing, and then we have everything until the final byte, until here. We have basically here, we have this situation, right? From the left to the right, we have this situation, and then we stop, and then this for loop stops. So at this point, the question becomes, how do we print everything else, this body, and this final element of the array? So the body, of course, is contained in the array S itself. So if we print the array S itself, we're gonna print the body. But before the body, remember that this array started with this preamble, right? And this is exactly what we print. We print 0. Here we print a tab 0, then a new line, then a curly braces, a semicolon, 2 new lines, and then the include itself. And with this, we have just recreated perfectly the program. And then here at the final thing here, we print a last 0 byte, which is like a null byte at the end of this file, and that's it. So basically, this is how we have this quine, and this is why it works. Now, of course, between the definition of this array and this block, here we can put any sort of code we want, and it's gonna self-propagate the same piece of code. So the logic does not change, and it is flexible in that sense. So yeah, this is what a quine is. I wanted to make this video to discuss about quines. I hope it was an interesting conversation. And in the future, I'm going to talk more about this article because I think that it is extremely interesting in the points that it makes and in the fact that if you hack a compiler, if you introduce a Trojan horse, a vector into the compiler, it can be extremely hard to figure this out. So thank you for watching. If you're interested in my content, you can subscribe to my channel, you can support me on Patreon, and also I have courses where I teach about security, about web application security, about Linux security, and in the future I'm gonna make more courses to teach security in different contexts. Thank you very much, and to the next video.